Okay, so we've been evaluating the integral, and basically we were doing the integral over to 3x. As I explained to you, it's an integral over an exponential, which gives you 2 pi cubed times a delta function. Now, the first thing that I want to point out is that there was a typo in the last lecture, the last recording, and the delta function that I have just underlined in red. This, in fact, I wrote down as delta K1 minus K2. It should have been delta K1 plus K2. So just check all of the signs very carefully. But I think that you should know enough to be able to correct all of the signs on your own and to come right on your own. So what are we going to do now? Now we will do the integral over d3 K2. So the logic here is we started off doing the x integral, okay? What has the x integral done? Because I was integrating these exponentials, I've got a whole lot of delta functions. And now that I've got the delta functions, it becomes easy to do the k integrals. Now, I want you to notice a few things, and this will show you why we've chosen to put the 2 pi's where we put them. So for each delta function, we got a 2 pi cubed. So there's a 2 pi cubed there. For this delta, there's a 2 pi cubed. And for this delta, there's a 2 pi cubed. And those cancel against the 2 pi cubed in the measure. Okay? So make sure you got each of these deltas. Each of them should have come with a 2 pi cubed. And make sure that your signs for the momenta in each of these brackets is correct. So all of the 2 pi cubes have canceled. And now something else cancels. You see, here's an omega k2. So this omega k2 will cancel against the omega k2 of that term, the omega k2 of the middle term, and the omega k2 of the last term. So omega k2 cancels out of everything. Now, when we do the integral over k2, the terms that I've underlined in red, so the first delta function and the last delta function, these will set. So let's say delta of K1 plus K2, when we integrate over K2, these will set K2 equal to minus K1. Remember, the delta function is only contributes when its argument is 0. So when K1 plus K2 is 0, which means K2 is minus K1. And these other two delta functions, so, well, for this middle term, the delta of K1 minus K2, what this will do, so delta of K1 minus K2, this will set K2 equal to K1. So when we do that integral, we just simply need to plug in these values for K1 and K2. One last thing that I just want to remind you of, I'm sure it's something that you know, but let me just remind you. If you have got omega k, well, remember, this is equal to k dot k plus m squared. But if we change k into minus k, because it's k dot k under the square root, that doesn't change. So omega k is equal to omega of minus k. So now let's go ahead and write down what's the answer of doing this integral. So we'll have equals to 1/2. We won't have the integral d3k2 anymore because we've done that integral. But we will have an integral d3k1 over 2 pi cubed, and we will still have the 2 omega k1. Then the only thing that's left from this measure is the 1/2, because we've cancelled the omegas and we've cancelled the 2 pi cubed. And in the first term, we've got minus omega k1. In the exponential, we must set k2 equal to minus k1, but omega of minus k1 is omega of k1. So we've got e to the minus 2i omega of k1t. And then we've got alpha of k1, alpha of k2. So that's the first term. I hope you're working along with me. Now let's look at the second term. Well, for the second term, we'll have plus omega of K1. That's still around. And in this term, we set K1 equal to K2, so that's fine. And then in the exponential, you see, if we set K2 equal to K1, then the I omega K1t cancels against the minus I omega K2t. So we get e to the power of naught, which is just 1. So that exponential disappears completely. And then what we've got is alpha dagger of K1, and we've got alpha of K1 again. Oh, sorry, I should actually, let me make a note here. Let me call this maybe K2 tilde on this first term. I'll call it K1 tilde on the first term, okay? So what is this? What is K1 tilde equal to? So K1 tilde is equal to, it's omega K1, comma, minus K1. So this is also 4 vector. Its zero component is the same as K1, but its spatial component is a different sign. And K1 tilde is what sits inside that oscillator. And it's happened because the delta function tells me to insert K1, K2 equal to minus K1. On the second term, I'm inserting K2 is equal to K1. So that's why I've just gotten an alpha dagger of K1 and alpha of K1. And then I'll have plus, oh, sorry, guys, there is another typo here. So let me just correct that now. So presumably, you got the second term without that dagger. Okay, so we've got alpha dagger of K1, alpha of K1, and then we've got alpha of K1, alpha dagger of K1. So this is what you should get for the middle term. And then for the last term, it's again a minus. We've got omega of K1. In the exponential, we set K2 equal to minus K1. So we'll get e to the minus 2I omega K1t, sorry, plus 2I omega K1t. And then we'll get alpha dagger of K1, alpha dagger of K1 tilde. Okay, so those are the four terms that appear. So these expressions are pretty long, but I hope the logic is easy. We started off doing the integral over x, and this was such an easy integral to do because we were just integrating exponentials that gave us delta functions. But once we had the delta functions, we could do the integral over d3k2, and this was an extremely easy integral to do because it's always easy to integrate over a delta function. And we've now obtained the expression that you see on the bottom of the screen. So I hope that you can all get this expression. Make sure that you can try to get it yourself.